As you have probably guessed, this any title is more of a marketing pitch than what we actually do. So it should have been getting access to any data that you normally have access to from any place and any time where you have network connection. So I'll start with telling you who we are and what we do, what we've already done, and what are our plans. And then I'll give some advice of how our work could be applicable to what people do on campuses and that need access to remote access to data. So we are an NSF-funded project. It's a 3-year project, and we're already halfway into it. We are paid for 3 people, but there are actually 10 people working on it, coming from UCSD, from University of Nebraska-Lincoln, and from University of Wisconsin-Madison. Our main line of involvement is the compact muon solenoid experiment at the Large Hadron Colider, but we also have really close ties with OSG, with Open Science Grid. I mean, more than half of people on the project are actively involved in OSG. There is also a sister project, FAX, from our competing experiment, ATLAS, but they are more focused on ATLAS themselves, and they don't work with OSG as closely as we do. So if I would have to say in one sentence what the project is about, it's to cover all aspects of remote data access in an organization with large-scale distributed storage and computing infrastructure. Now, high-energy physics in one slide. We bang things together as hard as we can, as often as we can, and then measure in great detail what comes out. That's why we have so much data, and that's why we need so much CPU power. And our final goal is to try and explain where the universe is coming from and how the heck it's even possible. The ultimate accelerator ever built, LHC, it has the physics potential of discovering particles up to 1 TeV in invariant mass. It has a circumference of 17 miles and lies on average 100 meters underground. And other than ATLAS and CMS that are shown here, and there are the general purpose detectors, there is also ALICE and LHCb, focusing on heavy ion physics and on B-meson physics, respectively. All 4 experiments, plus the people who take care of the accelerator, add up to about 12,000 people, some of whom are French. So now to the CMS detector. It is huge and heavy, but what matters most is that it is instrumented in detail. It has 80 million electronic channels. So if we could pump all this data out with the LHC collision rate of 40 megahertz, we could produce 10 petabytes of data per second. But this is not the truth, because we don't have the instrumentation, the buffers on the electronics itself that would allow us to do that. So we have a 3-level selection system that allows us to select interesting events. So what we are really limited by the amount of data we can store and process by our computing infrastructure. So we started running at 200 megabytes per second in 2010. By the end of this run, which ended a month back, we were recording at 400 megabytes per second, and we plan to run at 700 to 800 megabytes per second when the next run starts in a year and a half. So we are talking about up to 10 petabytes of data per year from the experiment itself, and we have approximately the same amount of data from our simulations, which we need to cross-check our theories and to understand background from standard model processes. Another thing, there are 2,000 people analyzing this data, and they come from 40 countries. So we have a serious problem how we can continue to analyze this data over the lifetime of the experiment, which is 20 years. So this is a politically correct version of truth. The fact is that, I mean, of course, we wanted to build a supercomputing center at CERN, but the founding agencies didn't give us money. So we ended up with having the computing resources scattered around the world. Second, we couldn't come together on the unique set of tools needed for managing data and for operating jobs. So we had a whole jungle of products lying around. And only now that, that the real data is here and the pressure for being in a production environment has been applied, this has become reduced to a manageable number of products. But in the meantime, we got really good at making these pieces of software talk among each other and to use common databases to drive the system. So we've been through several evolution steps in software. I mean, discarding one product and using another one. And we are confident that we can do that again if, when we scale up out of the comfortable range of certain software products. But what we did get right is having a global single sign-on security context using X509 certificates, and also this started to work well at some point, but caused many troubles. So this is the view of the whole CMS collaboration, and more importantly, the US CMS. The red dots are all the institutions, but we have one Tier 1 center at Fermilab, and then 7 Tier 2 centers scattered around the US, and 2 of those are in California, one here at UCSD and one at Caltech. Altogether, this is 20,000 cores and about 40 petabytes of disk. As you saw already on the talks yesterday, the first role of networks is to get data from CERN and then to the Tier 2 centers where it's analyzed. But also we have workflows where data is simulated at T2s and then pushed back to Tier 1s. So we use networks in all directions. What we were trying to do in AAA is to add a new role for networks by opening up all this data to access from anywhere. And first, this allows an easy access to people to do interactive debugging of data. To open a file remotely, just look at a small piece of data they are interested in, either in an event display or in a debugger, to see where their things crash. Then this allows us to squeeze the computing resources because we don't have to collocate jobs and data. And it also allows us a better usage of opportunistic resources where typically one doesn't get storage as easily as CPU. I usually joke that AAA is a meta project. Others don't like that much. But the reason why is because we decided explicitly that we will write no software. I mean, I told you before we had too much of things already. So we said we'll choose proven technologies, contribute back to them, and get them improved, and hopefully get it done for other people as well. So this is the list of 4 main components that we worked on. These are all hyperlinks if you want to follow up. So we have XRootD to serve and access data. We use Condor for flexible job scheduling, Gliding WMS to place jobs into job pilot slots, and CERN VM file system to deploy software. We started working with CMS, especially in the US, but most of the things we do are not CMS specific, so what we are doing should be able to be taken by others. And it's important, when we started setting these up, things were breaking. So we went through the painful thing of debugging things and doing the mistakes so you can learn from us. Okay, now the project status. So first thing that we had to do was to get our software stack optimized for remote data access. And here are just facts about what we do. All our software is firmly based on C++. And we use the root framework for object serialization, but also as an analysis studio for physics analysis. And it has a rather complicated format of data on the disk So, because our main goals are to optimize compression and to allow for access to partial data to do first the event filtering. So you want to pick events with the tracks with momentum more than something, so you can only read that column, and then when you know you have the events, you want to read them all to do full analysis. And this was a significant amount of work put into this, also not only from us, but also from CMS itself and from the root side. And what we did is we made the ability to coalesce successive reads into what we call vector reads, so that the round trip to the server and back is done once and not like asking for bytes. Another thing is develop the client-side caches so that they can do read-ahead and fetch data in advance. I mean, we can do that because we know rather well what we will be reading in advance, but it's not always feasible. Then the first big thing, of course, to kickstart this was to install and configure XRootD on all USCMS sites. One could say that this was just the matter of configuration, but there's always some fun with these things. And at this point, I would like to make some propaganda for the XRootD. If you don't know it, I mean, it's a great product developed at SLAC for the needs of the Babar experiment. And now it's being adopted also by all the LHC experiments. So it's a winner in performance, resiliency, in robustness. It's flexible. It has plugins for authentication, for file system access, and right now it's just being developed now is HTTP access, so people would be able to also send links to their files. It supports multi-tiered storage, which we don't use in AAA, but could. And it supports multi-site data federation, organizing them in a hierarchical manner, and it also supports peering between such federations. I'll show you an example in a minute. And it has an excellent monitoring, where you can really see what the system is doing on all levels. Now, as I said, it wasn't as trivial as it seems. It was about, I would say, 2 many years of effort from our side to make sure this all works as advertised, and also to adopt it to work well with the Hadoop file system, which is more or less standard on all tier 2 sites here. And during that, also the people from XRootD started to love us. So UCSD and University of Nebraska also joined the XRootD collaboration. And this is also being deployed now in Europe slowly on, I would say, about at this point at 30% of sites. So how does this work? We have a 3-level server hierarchy. First, there is a redirector or a meta manager, which is also the single point of entry into the system. So the user application comes and talks to the the user application, the client comes and talks to the redirector and asks him, okay, do you have this file? And he goes on and queries the lower level managers on the site. And here, there are also the disk servers, which typically on Hadoop, we have 10 to 20 of them. And at Fermilab, which uses Dcache, they have XRootD running on every server, so there's 350 of XRootD servers running there. So this gets propagated by the redirector, and it says to the client, okay, go talk to site A. Yeah, and then the client disconnects from the redirector and talks directly to the site and to the server that has the data. So it talks basically directly to the disk. The redirector will remember this query and will keep it in cache for a configurable amount of time. I think we use 4 hours. But if this is a wrong decision, so when a client comes then, and if the redirector thinks he knows, he'll put it down directly, but then the client sees it's not there, he'll go and tell to the redirector, hey, your data is wrong, and it will drop it from the cache, requery, and come up with the better answer, hopefully. And it's important, it's really important to have a coherent directory structure on all sites. XRootD does have plugins to do name-to-name mapping, but if you want to know what happens, go talk to our Atlas colleagues, which don't have this. Now, this is the peering capacity. As I said, we are putting this into production now. So, assuming that the file is not found in the US, the redirector itself can ask its peer in Europe, hey, do you have this file? And if this is found, again, this goes back, sent to the client, and client can then connect directly to the server in Europe. So this works correctly in a sense that if the file is in the US, it will be read from the US, and if it's not, it will still be read from wherever it is available. Now, the established usages, I already mentioned the interactive access and debugging. Then the second thing we do is fall back to remote reading. Most of the production workflows collocate jobs and data. And we had about 3% of job failure rates because the opening of the file itself failed. So at this point, I mean, it can be anything. It can be really that the file is corrupt, or the server is too busy, or it's doing something else and doesn't want to talk to us. So at this point, we fall back to XRootD, and if we can read remotely, we do. So this reduces the pressure on the production system. They would have to resubmit jobs and people looking at error logs and everything. And the third thing is overflowing to nearby sites. We have periods in typically before the conferences where some sites become heavily overloaded because they have the interesting data, of course, and everybody wants to analyze that. So they get queues that would be, the jobs would sit in there for a couple of days. And after 4 hours, we start bypassing jobs to nearby sites. I mean, we do this between 5 of the tier 2 sites at the moment. And also Fermilab. I think we added Fermilab last month. So jobs would go elsewhere and just read data remotely. On average, this is about 5% of our jobs, and in peak conditions, we've seen up to 30% of jobs at some site reading data remotely. But, yeah. Now, monitoring. As it says, we monitor everything that we can. And so beyond the normal things, I mean, is server alive? Is it serving files? Which is important because that's where things mostly break. The certificates or trust anchors get stale and things break. Then we monitor details of the individual servers, what they report about themselves, what they had for breakfast, how they feel today. And what we call the detailed monitoring is we really track all individual user sessions. So we see when a user opens a file, we see each individual request. In normal operation, we don't unpack vector reads. Remember I said that we coalesce consequent reads, and these have holes in between. So normally we only collect user requested at this offset and that many bytes, and this was made of so many chunks. But we have the ability, and we run this on a couple of servers, to completely unpack those. But this puts already, it's monitoring using more network than, not really, but that's how we feel about it a little bit, wasting it. Okay, so with all this data, we can then analyze the transfers and also file access patterns, how people access the data. And I say here, detect abuse, but we don't have abusive users. We only have ignorant and stupid users. And even that is not always true. Sometimes we really have a bad apple in our software, and then we go and we fix either in the CMS or in XRootD, and this hopefully solves it for good. Okay, some pretty pictures from our monitoring. This is almost a year of aggregated XRootD traffic out of out of our sites. You see that there are already some European sites in. But we have on average about 200 megabytes per second going out, and peaks with about almost 1 gigabyte per second. And if you know, the summer conferences are in July, and the winter conferences are beginning of January or end of December. So these peaks really correlate with the job overflow. We have very little new connection rate. I mean, as I said, we have about 20,000 cores. Our jobs last for about 8 hours, so you can do the arithmetic. We have about 1 hertz of connectivity, of new file open requests. And obviously, there is plenty of room to grow. And this is from Detailed Monitoring. It's a web page showing currently open files. This is our anonymized, so if you type this into your browser, you can see how it works. I mean, you don't know what files are actually accessed, just the beginning of the directory name, and you only get a user hash, so you don't know who it is. But you can see that that the things are updated regularly. So this one, for example, was just updated. And you can see that we know the average read. This is the average read request for which we need the detailed monitoring, and we calculate running average. But we have all the details, and we store this off to a disk so we can analyze in detail what people were doing. Now, what we are working on now, first is the caching proxy built into XRootD, which would support full and partial file reading, which we want to use for storage healing. As I said, I mean, file read fails, and we would like to use this, even if the read fails in the middle, we still open and fetch in the block, and we heal the storage, either with full files or with just blocks that went missing from Hadoop in our case, mostly. And once we have this established, we can do reduced and on-demand replication of data, because we know when we need it, we'll pull it in. I mean, it doesn't matter when we transfer it, or if we, so it will come in anyway. I'm taking my time. Is it okay since we saved some? Yeah. And another usage of this is having these caches installed on tier 3 centers at universities or use campus resources. So we don't have to use the full storage. We'll say, hey, use this box, and we know about how much disk we have to use. We are playing a bit with opportunistic usage and running on clouds, where we use the gliding WMS pilot jobs. So we queue them in, and when they're in, they phone home and say, hey, I have a job slot, send me work. And we use the CERN VMFS plus parrot. This parrot is not the Perl 6 parrot, but is a system called interceptor. So we can, there is a layer which sits between, in user space. So it can call, catch all reads and library opens and translate them to a network request over HTTP, and then it has local cache on disk. So you pull in as much software as you need, because our software installation is 8 gigabytes, and half of this is used by simulation jobs, half of this is used by reconstruction jobs, so it pays off not to pull in all if you don't need it. We did some preliminary tests on Amazon EC2, and our conclusion for now is that it's still cheaper for us to run on our own tier 2s, especially because of the network costs. Yeah, because we have to move data in and out. We don't have workflows where we could benefit from having data parked there. And the last thing is the having more flexible selection in the XRootD client or in the redirector of which source is used, and to be able to pull data from multiple sources simultaneously. And this is more or less done, I think, and we have to, I mean, it goes into XRootD client, so it's done for everyone. We don't plan to open any major new avenues. I mean, even in the proposal we wrote, year 3 we shall not start a new development. We'll fix what we are doing. We'll make sure all this is good and production quality, and we will run the stress test. I mean, as you saw, our usage is low, so we have plenty of room to push up, to scale up, to see actually start things breaking in new ways. And then we will pass over the operations to CMS. So as AAA goes, I don't have to sit behind the XRootD monitoring every day anymore. So take-home messages. So as I said, we are close to OSG, so all that we've done was put back into OSG and is available from OSG repositories. Another thing also, as I said already, is use XRootD to serve and access your data, but people should know, think about the geography of their federation, where they want to put the data, do they want to spread it out, do they want to have it localized, and also how to construct the namespace. As I said, if you can live with a single namespace across all sites, that's the best. And the important thing, authentication, what do people use? X509 certificates work well for us. XRootD also supports Kerberos and a couple of less kosher alternatives. Of course, people must know how they will read this data. I mean, where files will be read from to make sense from it. And in particular, they must know how the applications access individual files. Because on this, it depends if it makes any sense for them to do direct remote access, because then you really have to know how your application is reading the file and how to do read ahead, especially in I/O-bound applications. Otherwise, full file caching, if somebody's opening file, yeah, just copy it over and have it, might work better. So the last thing, if people decide to use XRootD, force them to immediately also install and use monitoring, because this would help them and you to understand what they're actually doing and allow them to fix their code and their access patterns, and make it work much better. You'll be able to detect file access error and user abuse, which I already said usually is not abuse, and you have a good system to do detailed accounting of who is using what. And of course, in the long run, it helps you not making fool of yourself more often than it's needed to. So in conclusion, the AAA, we are serving a large collaboration with having the big data to process. But we see, and that other fields are catching up. So, that's why we're sort of trying to shed it off and let you know what our problems are. And our project, we're focusing on real problems. We weren't reinventing the wheel, but, fixing what's there. So we hope that this can work for you as well. And if you're interested, we are completely open to collaboration, but especially through OSG. But you can as well drop me a mail, and we take it from there. Thank you.
This question is a little bit more about, the practical use. What size of file store or data store is basically fronted by XRootD, for instance? I'll start with that.
Yeah, our files are from 100 megabytes. These are typically very specific analysis subselections to 8 gigabytes, which is the raw data and the first level of reconstruction. So we have about a couple of million files. I would say more than 10 million, but less than 20 million in the US. That's more or less all the data is copied in the US.
So is that saying that it's more geared towards serving very large, relatively large files or file objects, or is it? Can you use it just as well, or is it for small files or many more small files?
Well, 10 million is a lot of files. So I would say this is not really a limitation of XRootD. I mean, it will shed the cache if it gets too big. I mean, typically XRootD would run happily in 1 gigabyte of RAM. And what did I want to say? Yeah, and the origins of XRootD are, it was actually designed first as a load balancer for objectivity, which was the great failure of, well, greatly depends who you talk to. But so it was actually done for small requests initially, and then they added the file system interface, and it became from load balancer a file system interface.
And then file ownership or access to specific files or specific subsets of your data. Is that implemented also through the XRootD, or is that just based on whatever's the underlying file system? Or
yeah, we have read-only access, and anybody who has a certificate based registered in a CMSVO is allowed to read it. It's possible to configure it differently. For example, I have our student use an NFS server for where they store all the data for their analysis, and I have configured the write access as well. So they can run jobs remotely and write the results back in through XRootD. And for them, I modeled this, and I just created a single user account for them and use group permissions for them to be able to write back in. But you can configure that in detail. But I can see your point here, that it might get unwieldy for thousands of users.
So generally, anybody, any person or any device with a certificate gets a view of the entire store. Okay.
Because otherwise it would be, we have 6,000 users, no, 4,500 with certificates. So, we map them to a single user before it gets to the XRootD. Thank you.